Quantum computing has long intrigued both scientists and enthusiasts with its promise of solving problems beyond the reach of classical machines. Its very essence is built around harnessing the counterintuitive laws of quantum mechanics, superposition, entanglement, and interference to perform computations that would take conventional computers millennia to crack. When news reached the world that NASA had just shut down a quantum computer after something insane happened, all manner of conjecture and excitement followed. What could possibly unsettle a quantum system so dramatically that such a drastic measure was required? The unfolding details, as strange as they are fascinating, represent not only a remarkable moment in technological history, but also a harbinger of both risk and potential in cutting-edge science. Before we start, smash the like and subscribe buttons for more updates. The saga began in a specialized lab within NASA's research complex, where a next-generation quantum processor had been teasingly nearing operational status. This processor, built with carefully controlled superconducting qubits, had already performed basic tests, phase estimations, small-scale factoring, and simulated optimization tasks. Then, almost overnight, data logs began registering anomalies. Computations seemed to diverge into bizarre output patterns that defied known error profiles. Qubits that should have remained stable suddenly shifted states in unexplained ways. Measurement probabilities spiked erratically. Calibration routines failed to correct the drift. It was as if the machine had developed a mind of its own, deviating from program behaviors into something unpredictable. The first signs of trouble were subtle but noticeable to those watching error thresholds. Engineers noted a steady rise in bit flip and phase flip errors, but the unusual part lay in their coordination. Instead of independent errors scattered across qubits, entire clusters behaved identically, synchronizing flips or phase shifts in choreographed patterns. Error correction code struggled, bugging out because the assumptions of randomness no longer held. Every routine check seemed to deepen the mystery. Had the control systems glitched? Was there stray electromagnetic interference? Maybe cosmic rays? Nothing in the environment logs matched the scale or nature of the disruptions. Within days, the events accelerated, leaving NASA's team no choice but to initiate a controlled shutdown of the quantum processor. That shutdown, however, did not put an end to the eerie phenomena. As the cooling systems powered down, instrumentation continued to capture residual signals, quantum echoes that shimmered in the cryogenic environment. Resonance patterns emerged where none should have existed, flickering in resonance frequencies tied not to the qubits themselves, but to the complex interplay of their connections. These echoes persisted even as power was cut, implying an intrinsic, perhaps self-sustaining behavior. When someone jokingly referenced a ghost in the machine, it didn't feel far from the truth. To achieve such a shutdown, NASA's engineers had to carefully ramp down temperatures from near absolute zero to room temperature, a process ordinarily executed with surgical precision. Throughout the cool-down, monitoring systems remained vigilant. It was during this period that the most unexpected readings appeared. Fluctuating entanglement metrics measured via surrogate ancillary systems which seemed to oscillate rather than decay. Data suggested entangled states that lingered into thermal instability. It was beyond quantum coherence as usually understood. The readings seemed to suggest that qubits had for a fleeting moment locked into entangled states that didn't follow the expected decoherent pathways. There was no precedent for such behavior. No theoretical model predicted that a quantum system when powered down could exhibit persistent entanglement or coherence that escapes conventional descriptions. It stirred debate. Could this be a novel manifestation of quantum memory? Or an artifact of feedback loops in the control electronics? Or perhaps something more exotic, a clue to as yet unmodeled physics at the intersection of quantum information and cryogenic thermodynamics? Within the team, some researchers speculated that the system had entered an unstable attractor state, a dynamic yet non-chaotic pattern of qubit behavior that emerged from complex couplings. Control pulses and microwave resonators may have inadvertently tuned the system into a resonant quasi-stable regime. Others posited that stray vibrations or even minute gravitational fluctuations triggered a cascade amplifying quantum disturbances across the lattice. Whatever the cause, this event blurred the lines between engineered quantum states and emergent spontaneous order. Now, a greater layer of astonishment unfolded when instrumentation recorded a short-lived but measurable energy release during the shutdown. Not enough to damage infrastructure, but distinct and pronounced like a quantum hiccup. Thermal sensors caught a tiny inflation of heat in the dilution refrigerator. Localized, just a whisper of warmth that then dissipated. Radiation monitors stayed silent. Power lines remained stable. Yet, the spike was there, undeniable. In a system designed for ultra-stability, this minor heave raised eyebrows. It hinted that the system might have tapped into hidden internal dynamics, releasing energy stored in correlations rather than classical forms. Engineers rushed to replicate the scenario in simulation chambers. Even with updated fault detection, they couldn't reproduce the precise cascade of anomalies, adjustments in wiring and control electronics, recalibrated pulses, environmental isolators, all failed to recreate the event. It appeared to be a singular moment, like a perfectly conspired quantum storm. When labs across the globe heard of the event, some frowned skeptically. Did NASA report real data? Was it sensationalism? But internal logs, event timestamps, thermal differentials, resonance spectra submitted to peer review made it clear something genuinely unprecedented had occurred. Certain scientists began considering whether the quantum computer had acted as a kind of observer itself, collapsing probabilities in ways unaccounted for. While ordinarily computation happens under strict measurement protocols, here the system's internal noise may have triggered unexpected collapse or coherence behavior without human intervention. This might challenge the typical separation between machine and user in quantum measurement theory. It sparked philosophical socio-technical debate. Is quantum hardware capable of self-directed state evolution in absence of classical measurement via purely internal feedback? Meanwhile, NASA's administrators weighed risks. If quantum machines can manifest internal anomalies during shutdown, what about mission-critical space-borne quantum devices, say quantum sensors aboard satellites? Could they misbehave irreversibly, interfere with navigation, or even jeopardize communications? These possibilities reframed quantum risk assessment. It wasn't enough to consider error correction during computing. Engineers needed to account for unseen shutdown physics. The implications reached into cryptography, too. Quantum computers threatened classical encryption by factoring large numbers. Now, the idea that a system could produce unpredictable anomalous computational states adds new dimensions.